So I'm going to walk you through our logic to find the mass of a single bead. And we started where you started, with the masses of the 4 piles of beads. Each pile had an unknown number of beads. But the first sort of intellectual realization that we had is that these mass values have to be multiples of the mass of a single bead. And if we could find the greatest common factor of these 4 numbers, that number, that greatest common factor number, could be the mass of an individual bead. The problem is it's not easy to find the greatest common factor when you're dealing with decimal numbers. If I have 2 numbers like 12 and 18, the greatest common factor of 12 and 18, you could probably figure out pretty quickly, is 6. Easy with just regular integers. Not so easy with decimal numbers. So the only clue we have at this point was these 4 numbers have to be multiples of the mass of an individual atom. The next step we took was, or the next sort of intellectual realization we had was, well, differences in the mass of piles of beads also have to be multiples of the mass of a single bead. So if you just think, like, let's say you have 21 beads and then 18 beads, and you take the difference of those 2 masses, well, that's going to be the mass of 3 beads, which still has to be a multiple of the mass of 1 bead. So differences of masses of beads are multiples of the mass of a single bead. Hope that made sense. I think I'm confusing myself a little bit, but hopefully you're with me. So once we had these 6 numbers, we had this thought: well, what if 0.96, the smallest number here, is the mass of an individual bead? Maybe there's only a difference of 1 bead between pile C and D. So if you take the difference between C and D, you have the mass of 1 bead. So if this is the mass of 1 bead, all of these numbers divided by this should give a whole integer value. So when we took the 1.92 divided by 0.96, we got 2. So that means that there could be a difference of 2 beads between piles B and A, which would be awesome. We'd be done. But then when we took the difference between A and C and divided that by 0.96, we did not get a whole integer number. And so 0.96 cannot be the smallest mass because it's not dividing evenly into these numbers. So the next step we took was, let's just keep going. Differences of differences still have to be multiples of the mass of a single bead. I'll say it again. Differences of differences still have to be the multiple of the mass of a single bead. These are all the differences of differences. And again, we had the same thought. Could the smallest value here, which is 0.48, which shows up 3 times, could 0.48 be the mass of an individual bead? And indeed, when you take the original masses and you divide it by 0.48, 2.4 divided by 0.48 is 5. So pile A must have 5 beads. 4.32 divided by 0.48 is 9. 6.72 and 5.76 divided by 0.48 is 14 and 12 respectively. So we have determined how many beads were in each pile. Of course, we went back and looked, and we saw, yes, pile A had 5 beads, pile B had 9 beads, pile C had 14 beads, and pile D had 12 beads. So unlike Millikan, we were able to go back and check and just count our beads. But we have successfully at least walked through the logic that Millikan employed, and we walked through the logic to be able to figure out the mass of 1 bead, but the logic applies to piles of atoms. So where does all this leave us? Not in terms of beads, but in terms of atoms. Well, hopefully, not that you ever doubted, but hopefully you are super confident that the universe is made up of atoms. All the matter in the universe is made up of atoms, and these are discrete, unbreakable things, at least when we're not dealing with nuclear power and nuclear physics. We'll get to that in some other course. But as far as chemistry is concerned, atoms are indeed unbreakable things. And in fact, scientists now know the mass of a single hydrogen atom is 1.67 times 10 to the negative 27th. That means there's 26 zeros before your decimal point. Kilograms is the mass of one single hydrogen atom. This is so small, and what this means is that there's 5 times 10 to the 21 atoms in a single droplet of water. 5 times 10 to the 21 it means 5 with 21 zeros. It's that number of atoms in a single droplet of water. So these numbers are so inconceivably small. No wonder we can have a little bit of empathy or understanding of why some scientists, many scientists, doubted and fought vehemently against the idea of atoms, because there was no way to even conceive of how small these things are. In fact, early on, John Dalton in the early 1800s had this idea of calling the mass of one hydrogen atom, which is the lightest element. Let's just call that 1. Whatever the mass is, let's just call it 1, and we'll make up a new unit. He came up with the idea of just call it atomic mass unit. Super creative, atomic mass unit. But then you could talk about every other element in terms of the mass of one hydrogen atom. So if we know that oxygen is 16 times heavier than hydrogen, oxygen would have an atomic mass unit of 16. If we know that carbon is 12 times heavier than one hydrogen atom, we know that carbon would have an atomic mass unit of 12. And one interesting point I have to bring up about the Millikan oil drop experiment, which is actually related to atomic mass. And again, he wasn't going after a mass, he was going after electric charge. But his data could be used then to find the atomic mass, not just with logic, but actually with the results of his data. So he found the charge of a single electron, but it was also known that hydrogen, the smallest element, the charge of a hydrogen nucleus is the same as the charge of a single electron, because there's actually only one charged particle in a hydrogen nucleus. So if you had a sample of hydrogen and you knew its charge, then you knew how many atoms of hydrogen were in that sample. And if you weighed that sample and you divided by the number of atoms in it, you could get the mass of a single hydrogen atom. So this was one way to figure out the mass of a single hydrogen atom. Just one final point I want to make, and this was only able to be made after reflecting on the 5 chapters in this course. And this was something that was not done by design. So when we developed these 5 chapters with all the labs in them, the idea was to let the history of the evolving idea of atoms be our guide in whatever experiments and thoughts were happening in history. This is what this was the experiments that we did. But just looking back, it's striking to me now that there's such a diverse set of approaches to science. Every single chapter, we did something so different from an experimental setup point of view. And it just goes to show that creativity and ingenuity are so critical in science. And just when you're going after an idea or you're trying to solve a problem, just bringing in ideas from anywhere and everywhere is such a powerful way to approach science. And just specifically, look at the conservation of mass experiment chapter 1. What we did there was use a mass balance analysis. In chapter 2, we use chemical tests analysis, the hydrogen test and the oxygen test. In chapter 3, we were doing something totally different. We were using electricity pulling from our friends in physics, and using the ratio of volumes of gases to make sense of the molecular formula of water. And then in chapter 4, we delve into something completely different, chemical kinetics, a whole subdomain, a whole major in college, or a whole subdomain of chemistry that people pursue in graduate school and in college. And then, of course, in chapter 5, we just went total mathematical, total thought experiment to figure out the mass of a single atom. So just an interesting reflection on, the tools and resources and intellectual efforts that scientists will take to solve the problems and challenges that they are wanting to solve and to face.